Next up is John T. Kevern. He's the chair of the Department of Civil and Mechanical Engineering at the University of Missouri, Kansas. He's going to talk about penetrating sealers' performance criteria on bridges, a new perspective.
All right, thanks much. Well, we've got the few and the proud here, right? But chair of Civil Mechanical Engineering, University of Missouri, Kansas City. And we've been doing lots of work with sealers over the years and helping different states, different entities navigate the minefield that is all things penetrating sealers here. So just quick, I'm going to show you some results and some background, and we've got done a lot of work with Wisconsin and Iowa, and we've got sections we were placing up at Min Road yet this year, and so we've done kind of lots of upper Midwest. So we know. So we can talk concrete deterioration till the cows come home. So we have lots of different mechanisms, but fundamentally it boils down to water in, aggressive ions in, and good stuff getting pulled back out of our concrete. So it is, if we're looking at bridge decks, we're definitely looking at chloride movement, water movement, freeze thaw. And so fundamentally, if we're thinking about our penetrating sealers, we really want to keep that water out. We want to keep our chlorides out. Part of this is coming along in that we've made some serious changes to our maintenance practices over the last 30, 40, 50 years. So historically, we say we didn't have the assumption, even say back to 1980, we didn't have the assumption every roadway, every bridge would be clean and dry during every storm, right? We had some of our roadways would be clean and dry, but now we have the expectation of sidewalks and low volume streets, and we apply massive amounts of de-icers in the middle part of the country and the north. And then if we get into sort of lower level streets and sidewalks, we could apply 10 to 100 times the amount of salt that we would on a roadway. And so we have increased our conditions so that those older bridges, it's not their fault. They weren't designed for it, right? And we've changed the game, and then we do something silly like, let's not apply rock salt. Let's apply a brine to our dry concrete, which causes lots of different issues, and now we have anti-icing to deal with. So let's take a look. Let's walk through this before we get here. So a couple different functions. We know this. We know concrete durability in freeze thaw fundamentally boils down to the degree of saturation. We know this doesn't matter what type of concrete we have. We get above somewhere around 85 to 90% saturation, and we're going to have freeze thaw issues. We're not going to survive 2-3 cycles without falling apart. And so things like lowering the permeability, air entrainment, these are good ways to keep that saturation down. But there's other post-construction, so we'll talk about the options for sealers. So what I'm going to say, though, and this is, we like to say, is penetrating sealers are very much like vitamins. So if you are fundamentally unhealthy, vitamins are not going to help you. If you are generally healthy, then they might help you. And so before we jump into this conversation of sealers, we just want to reinforce what's good best practices for making durable concrete. And so if we're talking about durable concrete, we want to make sure that we have proper drainage. So if we're talking bridges, we want to make sure our scuppers aren't backed up, our drainage isn't backed up. We want to make sure we're actually draining those joints and we're getting the water out. If we're making our concrete, we definitely want to use an appropriately low water to cement ratio. We've definitely got this over the last 30 years, but we do get into cases where because of strength gain or other requirements, we might get into really low permeability concrete, which usually has really high shrinkage, and that shrinkage cracking is quite permeable. So we want to make sure we use an appropriately low, but not too low water to cement ratio. Use our SEMs to optimize that cementitious hydration. We want really well-graded aggregates so we can reduce paste content. We want good curing so we have a nice impermeable structure. And we want an adequate air void system so we know now we can use the SAM or we can use some other techniques to make sure we've got a good air void distribution. And if we're doing sawing and sealing, not beat the crap out of our joints by using old worn equipment. We know this causes 2-3 times more damage than appropriate equipment. So let's make good concrete first, and then we can start talking about penetrating sealers. Okay, so this is really, we want to be fundamentally healthy, and then we can talk about vitamins. We're not going to be eating a bunch of McDonald's and fix ourselves that way. So just as a talk through, so this is a topic. If we throw out penetrating sealers, we got lots of different products. So if I walk through the exhibit area, I've got 5-6 different groups that are selling different products, which are penetrating sealers. We've got to understand the fundamental modes of action so we know, is this a good opportunity? Is this a good material for a certain case? So as we walk through, we have, I'll throw it here, kind of the first one is continuous films and barrier coatings. And so sometimes this is lumped into penetrating sealers, although most of the time not. So epoxies and acrylics and urethanes. These sit on top, they blind the surface. If we thin them out enough with solvent, you can get some penetration, but generally they're not going to fall in that penetrating sealer category. We kind of move on, we have pore blockers. And so these are materials that literally go into those pores and block water or chlorides from coming in. So fundamentally, if you go into your refrigerator or you go in your pantry, you grab some Crisco or some butter and you shove it into your driveway, you'll have a nice spot on your driveway that is waterproofed and it probably beads up water. That is a fatty acid, that is a good pore blocker. Probably not great or cost effective, but we're literally shoving something in there to block the pores. And so it doesn't get much more complicated than that. So what are we talking about? We've got different vegetable oils, we've got stearates, we've got absorptive silicates like we just looked at, sodium tartarates, which are sort of a different absorptive material, linseed oils, soybean oils, soy methyl ester, polystyrene, so stuff that soaks in but fills up those pores. And so some of these, as we mentioned, it was just mentioned before, some of them just hang out in the pore. So if I take some fatty acid and I put it in there, it's generally going to be stable for a while. Some of them absorb water, and then if there's a long time passes, it gives it off, it sort of shrinks, it breathes, then water shows up again and it sort of blooms and replugs that pore. We have this class of what we call pore refiners. So this is one where 10 years ago or 15 years ago, it would be common to only use sodium silicate densifiers in polished floors. So we've used sodium silicates in polished floors for getting on to about 100 years now. And so that silicate goes in and reacts with our excess calcium hydroxide. And if we use this, we put this on the surface, it literally refines or shrinks those pore size up. And so we've got sodium silicates and lithium silicates and colloidal silica, and we've got different versions, different things on the market for both interior and exterior. And I'll kind of put an asterisk there that a lot of times these are combined with some sort of a hydrophobic agent or a pore liner. And this is as we kind of move on to our next class, is we're going to use some chemical lining to reduce the attraction of that water to our concrete. So concrete is naturally hydrophilic. It both chemically and physically attracts water because of the pore size and the chemistry. So when it's going to rain here later, which normally doesn't, but the concrete outside is all going to get dark because it soaks up water. So the idea with these pore liners is they're very thin chemical agents that are a molecule or two thick that line the inside of the pores, don't really block the pores, don't really make the pores any smaller, but they are going to chemically repel those materials. And so this is typically we're looking at silanes and siloxanes and siliconates. And I'll kind of throw out there with this is our solids effects. You can buy products on the market with 1% solids, and you can buy products on the market with 99% solids. The carrying solutions are different, so some are carried in a solvent, some are carried in a water, and so we just have to pay attention to application rate, and we have to pay attention to solids and depth of penetration and things like that. Depending on the chemistry, they can react with certain parts of our hydrated concrete to physically bond. Others just sort of hang out in the pores and go away. So lots of different versions on the market as well. So we say, so what? So somebody walks in your door selling magic juice. So we want to evaluate, does it work, right? I mean, this is the second I say we're going to do any sort of sealer work, I have more buckets of stuff show up at my doorstep with all kinds of, every claim in the world. It's sort of, does my taxes and waxes my car and does everything in the world. And so to help what we've been spending a lot of time helping DOTs is like, let's just cut through this. Let's do some simple testing to see, well, is it real? I've got buckets of stuff that is literally nothing more than blue dyed water. But the story is, we just don't have sophisticated enough testing to tell that it's working. You know, that's baloney. I got like $2 million in equipment in the lab. We do stuff all the time. Don't give me that business. All right, so is it real? Is it there? I spray some clear thing on my concrete. How do I know it's there? Is it doing anything? How do I know it's still working 5 years from now? When we worked for the state of Wisconsin, they said we've been applying Silanes for 20 years. We don't even know if it's still working. Well, we didn't verify it first, and we're not. Okay, so it's basic things. And what I'm going to walk through here is how can I quantify with mortal testing? Okay, this is, DOTs most often do not have hugely expensive pieces of equipment, and what I really get tired sometimes with academia is if I get myself $1 million piece of equipment, all of a sudden everything looks like a nail to that hammer. And then I start showing all these results, and we don't know, is that something new, or is that something we're just seeing for the first time, and then you say, you can't afford it, don't know how to run it, and so don't worry about testing it. So what I'm going to focus on here is like cheap stuff that you can do, easy things, and we're not going to bring out too many differential equations to help explain the process here. And sort of the other thing I'm going to throw out here, if anybody has ever done anything with sealers, this is sort of my biggest pet peeve in the world. I'll get sealers delivered that say they meet NCHRP 244. As concrete sealers for protection of bridge structures, it is a report. It's a report. It is not a specification, and it is not a test standard. You can't meet a report, this report, any more than you can meet volume A in the encyclopedia. It is information. There are tests in there. Most of those tests are no longer current, and so we can use this as guidance, but we cannot meet a report. And so if you see that stamped on the side of your bucket, it should be sort of the first red flag to know that they're totally full of crap. All right? So now that I've told everybody that the Easter Bunny and Santa isn't real, let's actually talk about what we want, though. So we do want to reduce water movement into our structure because we want to maintain a lower degree of saturation to have better freeze-thaw durability. We really want to reduce chloride movement in so we can extend that time to our critical chloride threshold so we have longer durability. We don't want to impede water movement out. So if my structure gets saturated, my pavement gets saturated, the last thing I want is something in there that keeps it from drying. Now I've extended my time to critical saturation, and now I have more chance of freeze-thaw durability. This is one of the mechanisms why salt is so bad, because it changes that drying phenomena so it stays wetter for longer. So, and then we don't want it to degrade too quickly. And so I can take, and because there's so much silane out there, I can take 1% silane, put it in some rubbing alcohol, spray it on your concrete. It will bead water fantastically for long enough for me to cash my check. Okay? It probably hasn't penetrated enough. It is not UV stable enough. It wears off quickly, and so we want it to be there. However it's functioning, we want it to be there. So I'm going to show you some information here to keep my number of emails and phone calls down for the amount of people asking what we used. I will call out a couple products. I'm not saying we're advocating for them or we're not. We're just showing information. There's lots of products and lots of different functionalities. So Silanes. I'm going to show you some information on Silanes. 40% silane is pretty common for DOTs. Because circa 1980, that was a pretty stable, cost-effective material. We've looked at less. I've looked at a lot more. I will tell you, I'm pretty happy with 40%. Either solvent or water-based, they both function pretty good. Okay, so 40%. And I say the brand there, XXX, because there's not too many raw material suppliers of silane. They're all basically coming from the same place. Other things that a lot of states are looking at, and I know Paul's got a version. They'll be, I think, Pore Shield probably will be talking tomorrow. But this is, take a soybean oil, you basically crack it and then use it as a solvent to dissolve polystyrene. So think pop bottles, okay? So this came out of Indiana, but there's different versions out there. So think solvent carried plastic. And then lithium silicates are densifiers, and they're usually or a lot of times doped with a hydrophobic. Consolidex, the one we've used here, there's a bunch of different ones on the market that are out there. And then sodium tartarate is another one that we've used. So sodium tartarate's an absorptive mineral, and then this one's particularly has a little bit of hydrophobic to it as well. And so Pavix is the version of that we've used. So kind of notes on concrete as we move in here is a lot of times sealers are used on good concrete, and especially when we do research, all of a sudden the best contractor is on their best behavior, and you get really good concrete, and when you've got really good concrete, it's hard to determine, have you done anything? And so often for research, you've got to actively make bad concrete, which not folks really, they generally don't want to do. So Iowa actually let us make some bad concrete. And so for a study we're currently wrapping up, we made concrete that had pretty marginal air system. We made concrete that had a known decracking aggregate in it. And then we made concrete that was oxychloride susceptible specifically. And so we changed one thing and then we could evaluate. So if you see some of the other ones, I'll show you sort of three concretes. And kind of the key is if my concrete's not great, if I have a bad air system, can I apply a sealer to make it better? That's a good question. I mean, it makes good concrete better, but what if I have maybe not so good concrete? Step one, so this is an easy 4-step process we'll go through here. So we want to look at water in. This is one of our favorite, absolutely favorite tests to look at. I take a puck of concrete, I seal the outside with butyl rubber tape, I put a little shower cap on top of it, and I just put it in contact with water, and it sucks up water. And you get this nice, on the right there, we've got this nice trend where in the first day or so, all your little pores, your capillary pores soak up water, then it gets saturated, and then it switches over, and you start getting into diffusion, so it fills your air and train pores. And so based on when that nick point or that transition happens, you get an idea of the size and number of your pores. And all I'm doing is letting water soak up in my concrete and measuring it. Pretty cheap, pretty simple, and you get a general look like this. So it absorbs with time, and here we can see for our example, the top is our untreated concrete, and then we've got various different applications of sealers, and you can see that total absorption comes down. Makes sense. Less water in, it's going to be longer, and it's cheap. I can look at it, I can compare. Did it do what it's supposed to do? Other thing we're going to look at, and you've got our, if we're going up here, sort of my left is my pore air concrete, the middle is my oxychloride susceptible, and the right is my decracker. We look at our control soaks up water, And then all we do here is once it's soaked up water, we flip it back upside down, let it dry out. So we look at water in, water out, and kind of the key here we'll talk through is, in this case, we've got our sodium tartarate and our soy methyl ester here. We've got absorbed less water and then dried out back to our control. And our silanes on all three different, here's our samples, dry out, and our silane here. Our silane, we basically lose that initial absorption because we've waterproofed all those little pores. So our inadequate air, we have absorbed less, we've dried out. Our oxychloride susceptible, again, we've absorbed less, we've dried out. And here is our decracker, and it's kind of interesting in our decracker, the pores are a little bit different, and our pore blocker in this case actually impeded the drying of that concrete. So we can take a look at water in, water out. It's hard to compare apples to apples with this because they've absorbed different amounts of water, so they're at different degrees of saturation, but we can kind of see comparatively where they're at. So to get them to the same level, then you can take those samples, you can put them in a vacuum chamber, and you can vacuum saturate them, pull them out, and dry them up. And if we look at that, we're looking at our absorption against our different materials, and we can see our time to our critical saturation there of our samples, and we can measure our time to that 85%. And depending on the material, we get 2 to 7 times increase in time to critical saturation. So we think that's pretty good shape. And then if we take those, we saturate them, when we dry them out, we can look at, from a 100% saturation standpoint, we can look at drying here. And kind of the key is our inadequate air sample, our tartarate or our absorptive material there, pore blocker gives off our moisture. In this case, our silanes and our pore blockers impeded that drying process. Same thing for our oxychloride, same thing with our decracking. So we can look to see if degree of saturation is a concern and I don't want to increase my freeze-thaw potential. Maybe we do want to worry about what that drying condition is. And a third thing we can look at, we can definitely look at contact angle. And so especially on these hydrophobic materials, we're going to see what they've done to that surface tension in our concrete. And there's really expensive pieces of equipment. I had a faculty come to me the other day, wanted to buy a $30,000 specialty camera for this, and I said, we're using our phones and pretty cheap or free software, and I can get pretty close. And so this is if someone says they are a waterproofer, put a drop of water on it and measure it. Pretty cheap and easy. We can quantify it, and we know that higher angles mean there is less surface tension, so it is going to be a rounder ball, and so we can measure contact angle. Is it there? Is it still working? Okay, definitely we can do that. Step 4, we're looking at chloride penetration. This is, again, not a real expensive test. Take my sample that's been applied with sealer, you put a dam around it, you put a salt solution on, you let it absorb for 90 days. So this is AASHTO T259, T260. You let it soak in, you grind through, and you measure what the chloride levels are at various profiles. Pretty straightforward. If it's working, it should keep out my salt. And so T259, 260 kind of averages that first half inch and that second half inch. And you can kind of see our control here, the top piece and the bottom piece for our control. And we can say, oh, our silane applied to a dry concrete had a pretty good reduction. Our silane applied to concrete 30 minutes after sawing, so to a relatively damp concrete, less effective. We can look at, say, our siloxanes of various combinations, not so effective. We can say, well, in this case, we used our curing compound. We just sprayed our curing compound on our sample. Didn't do a bad job blocking. Got other absorption issues and freeze thaw, but for chlorides did a pretty good job, our soy methyl ester. And so we can say, you don't have to take my word for it. Pond salt on it. We can get a chloride diffusion for that. I can put that in my life cycle models to know, have we improved our durability? Kind of the last thing I'm going to throw out there is this kind of boogeyman that is out in the industry right now, that is calcium oxychloride. So calcium oxychloride is a transient, expansive mineral reaction between our calcium chloride or secondary calcium chloride and our unhydrated cements. It's kind of hard to see at the time, but you see afterwards those expansion causes some serious problems. And so this is one across the country. We've been seeing more of this now that we're looking for it. And so the question has this always been causing problems, or is this because we know we're looking for it, we're seeing more, but we know it's an expansive product, we know that we're having some issues, and you say kind of the key there is the left is our control, and that bar is high. High means a high potential for oxychloride, and then everything below that are various families of sealers. And so those reactive silicates basically consume all of the calcium hydroxide, so you've got a really low potential for oxychloride. But kind of the key there is, do sealers help if we think this is a problem? Yes, they help. And so there's been good work out of Washington, and I think Minnesota, and I think Indiana has come out with some, and sealers do a very, very good job in protecting us against oxychloride formation. So we take all of these data, all this information, and then we can tie it together, and we can then predict our time to critical chloride, critical saturation, and actually quantify, if I applied this, do I get a good return on investment? Is this a good cost benefit? And we haven't, and you don't have to take my word for it. You can go out, you can test it. It's easy stuff to interpret, and we can move on from there. So kind of thoughts and recommendations here. So just keep in mind, we've got a wide variety of chemicals and products out there, and they all claim to do something spectacular. And so just put your antenna up and listen. They do not function along the same pathways. Some are good when they're applied early to concrete. Some are more appropriate for later age concrete. Some are good for really deteriorated concrete. Some are terrible for deteriorated concrete. They cause more problems. And just meeting NCHRP 244 is not going to tell us anything. We're not putting it under our pillow and sleeping well. Okay? So I'll say at a minimum, we can measure absorption, we can measure desorption, we can measure that desaturation, we can look at contact angle, we can look at chloride penetration. Don't cost a lot, and they don't get real hand-wavy. It either is working or it is not working. Other things, corrosion initiation, scaling, one-dimensional, if we ran the Rylem freeze-thaw, oxychloride could also be beneficial if interested. So those get a little bit more expensive, a little bit more lab-specific. And so just kind of there's a lot of different groups, really good groups doing work on sealers. So there's good work out of Nebraska. Glenn Washer will be here tomorrow morning from University of Missouri talking about some sealers there. Wisconsin, Minnesota, Arkansas, everybody, Clear Roads, lots of good work. And so I'd say the body of evidence is out there to really justify that these are value added for our concrete. So I'll say the value proposition, the technology, and the test methods are here. And so it is something we should be looking at here for the future. But kind of the last thing is we definitely don't want to have this as a reason to not make good concrete. So we want to make good concrete first. So with that, we were up putting some bridge deck sealers out on some samples at Min Road here recently, and so we definitely appreciate all of the partners. And if you're interested, we got lots of information. If you just search online, all the reports are out there, or you can shoot me an email, and happy to pass it on.
Let's put our hands together and give John a round of applause. Thank you, John.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.